Okay, so for the rest of the week, we're going to be talking about vector valued functions. So for the next few days, we are going to be looking into chapter 12 with all of the two-dimensional stuff. Today, I think you have book work, but then the next couple days, you have some worksheets. Okay, we will end up quizzing next week. Okay, next Tuesday, I think, and then we have a test the end of the week, and then it's our final. Okay, so we have a vector valued function quiz. We have a chapter 10A test, and then a final. Okay, so we are basically going to take what we learned with parametric equations and what we learned with vectors and smush them together for vector valued functions. Okay. So here's our set of parametric equations, and we force it into a vector valued function.
Yeah. So the objects. Yeah, I got 100 on it.
No way.
Oh, that will a little more than that. According to you derive the equation wrong for all the tissue Ross the raw score of 3%. It went up to a 54. How do you get a 3%?
What was your round form?
100.
Jessica said the mode in your class was 1.
Yeah, well, you get like 3 kids, you get 1%. No, it's 1 out of like 36 or something.
That's hard.
What? It's not bad.
Mode in my class was 100.
Yeah, because there's 2 kids who got 100 in your class, and then I got 100 in my class. It's like test.
Okay. So let's talk about this whole vector valued function business. Okay, so basically what's going to happen is we're going to put in like t equals 1, and that's going to give us this vector right here. Okay, and that gives us a coordinate on our curve. Okay, and then we plug in 2 to our vector valued function. That's going to give us a vector that points to a coordinate at t equals 2. So these vectors are basically tracing out our curve for us. Does that make sense?
Yeah.
Yes.
They always start.
Yes. Grace, how is that southern sunshine? You look like you have some nice color. Thank you for bringing the warm weather back with you. Yeah. Can you believe this? It's going to be the first week of December and we have highs of 60s and 70. Like, what? Is it? No, I don't. All right, so go ahead and write down these parametric equations right here. And we're going to talk about what the vector valued function would look like. So our vector valued function would be cosine of t I plus sine of t j. We're basically taking the set of parametric equations and writing it as a vector function. Cost. Okay, so let's talk about what this is going to give us. Okay, what would P of 0 be? 1.
I.
Okay, so that gives us this vector that leads us to that coordinate. Okay, what do you want to plug in next? Do you? To cosine and sine? What did you say? I can't hear you. Pi over 2 sounds good. When we plug in pi over 2, what's our vector? Okay. What else you want to plug in? And what's our vector at pi, Josh? Where is this going? Oh, so we're going to have a circle. And we have orientation that's going counterclockwise. So we're still graphing parametric equations, okay? We still have that orientation. It's just defined as a vector value function, okay? Are we okay with that? Why would you mock me? No, you're being a jerk. Don't. Okay, write this down. We're gonna talk about this. Okay, so how do we determine the domain of a vector valued function? Let's start with looking at each piece separately. What's the domain of the sine of t? Okay. What about t to the 1/2? What would that domain be? 0 to infinity. All right. So when we're looking at the domain of the entire vector valued function, we want to look at where these two overlap. So where do these two overlap? 0 to infinity. Many of you struggled to get out of bed this morning. You woke up at 3, like for the day. Okay. All right. We're gonna graph this guy right here. Now, it is not very efficient for us to just like plug in coordinates, okay? We still can go back to how we graphed with parametric, where we eliminate the parameter, right? So in this case, we know that X is 2 cosine of T and Y is sine of T, okay? So if that's our set of parametric equations, how do we eliminate the parameter? Normally, I would say solve for T, but in this case, we have a different strategy. When
It's a circle. Not a circle, it's an oval. It's like
ellipse,
cosine is weird.
we know that cosine squared plus sine squared equals 1. Well, cosine is the same as x over 2. Sine squared is the same as y squared. So this oval, you say, is it longer horizontally or vertically? Good, how do you know? Okay. It's not a bad way to think of it. Okay, so 4 is underneath of x squared, which means from our center, we're gonna move out how far? 2. 1 is underneath y squared, so vertically, we're gonna move out 1. That's good enough. All right, now, how do we know what orientation to choose? Straight? What? Like, bad joke. How do we figure out our orientation? Plug in numbers. What happens when we plug in 0? What happens when we plug in 0? We're at 2, 0. Right? What happens when we plug in pi over 2? We're at 0, 1. So again, we are going counterclockwise, but don't assume that, okay? Don't assume counterclockwise, please check. Well, if one of them were negative, yeah. As long as these are both the same, yes. But once you start getting, like if one's T and one's 2T, you're probably gonna wanna check. Okay, if I ask you to find me the limit of a vector valued function, then we can take the limit of the horizontal component separately from the limit of the vertical component. Now, I probably could have just asked you to find the limit of a vector valued function and you would just do this anyway, but here's the official definition. I'm gonna go ahead and do this limit right here when you have written down what you need to. Okay, the limit as t approaches 0 of e to the t. Dane, what is that? No? What's e to the 0? Andre, what about sine of t over t? What do we have to do? So cosine of t over 1 gives us, oh, that's boring. So this limit gives us 1, so we have 1i, plus this limit gives us 1, so we have 1j. So our limit is the vector valued function I plus j. I'm trying to make my i's and j's bolded. It's totally fine if you don't. I just want you to understand that that's what I'm doing. Okay. All right, continuity of a vector valued function. I love continuity. Is this somebody's Nebraska sweatshirt?
He was on.
It's not yours. Who? Yeah. We have a piece of Evan here with us.
So he-
You guys are weird. I commented that there's a sweatshirt that looks like Evan's sweatshirt. There's a piece of him here with us. Okay. There are 3 things that imply continuity, and you should know these from a year ago. What's one? Okay, so in this case, R of A exists. The limit exists, the function value exists, and they are the same. Okay, so you and one other person at your table, I want you to talk about where this vector valued function is continuous. On what piece of the domain is this continuous?
Yeah, we're supposed to do math, or you're supposed to.
Just look at it.
We have two, no, we have two more. Well, we have two more tests, but yeah, we have two more units.
Okay, Grace and Rachel, what did you decide? One, just at one? One to infinity with one or without one? Good guess. Wasn't a guess. You knew. You knew. Okay, we can take the square root of 0, so like 1 is fine. Okay. We have continuity everywhere where there's domain, because we don't have any asymptotes or holes or anything like that. Okay, this one has domain 0 to infinity. This one has domain 1 to infinity, but they can only overlap at 1 to infinity. Okay, all right, your pencils can take a break for right now. Okay. Yeah. This is the definition of a derivative, correct? Okay. So let's talk about what if R is f of t I plus g of t j. Okay. Well, then this would make this the limit as h approaches 0 of f of t plus h I plus g of t plus h j minus r of t would be f of t I plus g of t j all over h. Okay, well, let me go ahead and rearrange this. I'm gonna group my i's together. So f of t plus hi minus f of t I plus we have g of t plus h j. This distributes to be a minus g of t j. Okay. So if we have the limit as h approaches 0 of this, what does that mean right there? F of t plus h minus f of t all over h, the derivative of f. So we have f prime of t I. What does that mean? Oh, cool. So if we have a vector valued function, then its derivative is just the derivative of the horizontal I plus the derivative of the vertical j. Now, would you have assumed that? Probably, but now we've talked about it officially. And the more time I waste on these little things, the less we're going to cover in a day, right? That's all. Okay, so here is our example. Write it down, find the derivative, compare it to a neighbor. Compare it to a neighbor. All right, Evie, what'd you get? Good. All right, so let's talk about this. I want to look at this graph. So if we made these into parametric equations, x equals t and y equals 4 minus t squared, okay? So if we eliminate the parameter, we would have y equals 4 minus x squared. Do you agree?
Yes.
Simple yes or no. Thank you. Oh, it goes on here. Okay. So we have okay, and our orientation is this way. All right. So if I asked you to evaluate r prime of 1, first of all, what would that vector be? I minus 2j. Okay. Now, if t is equal to 1, what coordinate would we be at on our parabola? What? Plus 3j. Okay, so that would be right here. So our vector of 1i minus 2j is our tangent vector. Hey, that looks good, right? If we draw our tangent vector from the coordinate, we have, it should be tangent, right? What would you call this vector right here? Okay. Our normal vector. This is a tangent vector, then this is our normal vector. But yes, those two vectors would be orthogonal, which means their dot products would be. Okay, you remember something from last week. That's good. Okay, on your quiz, you had a question in which I asked you to figure out if there was any places where the curve was not smooth, right? Okay. So if we have a vector valued function, f of t I plus g of t j, then we are going to be not smooth anytime f prime of t and g prime of t are 0 at the same time. So it's going to be the same concept. We're just working with a vector valued function. So we're just getting the, it's just presented to us in a different way. So then this is the example that we're going to work through. And then we only have one more topic to talk about. What do you think comes next? That's going to come on Thursday. 12.3. On Thursday, look, it says velocity and acceleration. Okay. I was talking about like today. We have one more topic. What do you think comes next? Yes. All right. So is this a smooth curve? Well, f prime of t would be 1 plus cosine of t. So essentially, we want to know where the cosine is -1. Where does that occur? Not pi. Yeah. 3 pi, 5 pi. Okay, we have to make an entire rotation, oops, around the unit circle to get back to that -1 for the x coordinate. Okay, now over here, g prime of t is negative cosine of t. Well, how about just positive cosine of t? Okay, that's fine. Whereas this equal to 0. Okay. All right, so is there anywhere where this is not smooth? Okay, this is a smooth curve because dx dt and dy dt are not simultaneously 0. Okay, is essentially what that's coming down to. Okay, we have one more topic to get through. Before we do, you're gonna tell me what the best thing you ate was on Thursday.
You have that in down here.
Tacos. They dropped them on the- I told you never.
She was in there.
Like,
We went to a movie at the Alamo Draft House and we ate popcorn and we got some refills on our popcorn. Me and my 2 boys went through 3 bowls of popcorn. That was our dinner though. No, that was our supper. Let's get through the next example and I'll show you what we did for Thanksgiving because we did a little bit of a non-traditional Thanksgiving. Okay. All right, this is our last concept. Yes, integration. If we have a vector valued function, then we are going to integrate the vertical and the horizontal components separately.
when it's like loading the game, it displays like the graph on the board. Yeah. No, like polygraphs, like a concept in that. Yeah, it's not good. It's all like. Yeah, what is this used for?
You wait until over the next couple of days, it'll become more apparent. Okay. All right. So here's our example. Yeah, so what we do is we're going to have the integral of e to the t dt times I plus the integral of sine of t dt j. Okay, Remember, these are indefinite integrals. So what is the antiderivative for e to the t? E to the t plus c. The antiderivative for the sine is negative cosine of t plus c. Okay, now notice how we have a constant times I plus a constant times j. Do you see that? Yes, that's what I wanted you to figure out. So what we have is we have a constant vector. Do you see what I'm saying? We have a constant vector. A constant times I plus a constant times j, that's a constant vector. So constant and a constant.
Yeah.
And since they're in vector form, we can just say that this is a constant vector. So, you know, for your plus C in unit 4 last year, we would like solve for a number. Well, anytime we solve for this, we would be solving for a vector. A comma B. Well, I mean, yeah, this is just easier. We'll work tomorrow with like actually solving for that plus C. Okay.